Listening practice, a more detailed expansion of Chapter 1, Advanced Calculus for Engineering Analysis, structured for maximum clarity and practical relevance for civil engineers. Chapter 1, Advanced Calculus for Engineering Analysis 1.1 Multivariable Calculus and Partial Derivatives Core Concepts, Partial Derivatives of Functions with Multiple Variables, f/x, superscript 2 f/xy, Total Differentials and Exact Differential Equations, Chain Rule for Multivariable Functions Engineering Applications. Stress-strain relationships in 3D materials, Hooke's law in tensor form, heat transfer analysis in building materials, Fourier's law with T/x terms, example, calculating thermal gradients in concrete curing processes. Visualization tools, 3D surface plots of stress distributions, contour maps for temperature gradients in structural elements. 1.2 Gradient, divergence and curl in vector fields. Mathematical foundations, gradient, phi, for potential fields, e.g., hydraulic head in groundwater flow, divergence, v, in fluid continuity equations, curl, times v, for rotational flow analysis. Civil engineering applications, gradient applications, slope stability analysis, z for terrain modeling, divergence theorem in pipe network hydraulics, curl in wind load analysis on structures. Case study, using gradient fields to optimize earthwork cut and fill operations. 1.3 Applications in fluid mechanics and stress analysis. Fluid mechanics, Navier-Stokes equations. Simplified forms for civil applications, Bernoulli's equation derivation using calculus concepts, viscous flow between parallel plates, code flow, stress analysis, Airy stress functions for 2D problems, calculus of variations in beam deflection problems, Moore's circle derivation through differential geometry. Computational methods, finite difference approximations for derivative terms, MATLAB examples for solving superscript 2u/x superscript 2 equals f, x, boundary value problems. Practical workshop problems. 1. Calculate the gradient of a road elevation profile to determine drainage requirements. 2. Analyze divergence in a stormwater runoff model for urban planning. 3. Derive stress components from a given displacement field function. Special feature, from math to construction, how differential calculus underpins modern BIM software algorithms. Interview excerpt, how I use multivariable calc daily, a structural engineer learning objectives checklist. Master partial derivatives for material property modeling. Apply vector calculus to fluid flow problems. Translate stress equations into computational solutions. This chapter structure provides 1. Rigorous mathematical foundations. 2. Direct civil engineering applications. 3. Computational implementation. 4. Real-world problem solving. Would you like me to add more detailed fluid mechanics examples? Additional computational methods? Specific case studies from notable projects? Here's a comprehensive expansion of Chapter 2, Linear Algebra and Matrix Methods, tailored specifically for civil engineering applications. Chapter 2, Linear Algebra and Matrix Methods for Civil Engineers. 2.1 Matrix Operations and Eigenvalue Problems. Core Concepts, Matrix Types in Engineering, Symmetric, Banded, Sparse, and Diagonal Matrices, Eigenvalue Decomposition, Lambda in Vibration Analysis, Natural Frequencies, Special Matrices, Stiffness Matrices in Structural Analysis Engineering. Applications, Stability Analysis of Structures using Eigenvalue Problems, Principal Stress Calculations via Matrix Diagonalization, Buckling Load Determination for Columns. Computational Tools, Python code snippet, Solving Eigenvalue Problems with NumPy, MATLAB example, Eigenvalue Extraction for a 3D OF Structural System. Visual Guide, Graphical Representation of Eigenvectors in Bridge Mode Shapes, Matrix Sparsity Patterns in FEM Models. 2.2 Solving Systems of Linear Equations, Finite Element Applications, Solution Methods, Direct Methods, LU Decomposition for Structural Systems, Iterative Methods, Conjugate Gradient for Large-Scale Problems, Condition Number Analysis for Solution Stability. Finite Element Implementation, Assembly of Global Stiffness Matrices, Application to Truss and Frame Structures, Handling boundary conditions in matrix systems case study, solving a 1000 equation system for a steel building frame, comparison of solution times, direct vs. Iterative methods practical workshop, 1. Solve a plane truss problem using matrix methods. 2. Implement Gauss-Seidel iteration for heat transfer analysis. 3. Analyze ill-conditioned systems in foundation settlements. 2.3 Coordinate transformations in structural analysis. Transformation types, rotation matrices for member stiffness, local to global coordinate conversions, transformation of stress/strain tensors. Engineering applications, analysis of skewed bridges, transformation of wind load components, global stiffness matrix assembly. Advanced topics, homogeneous coordinates in structural modeling, quaternions for 3D structural rotations. Tensor transformations for anisotropic materials. Special feature, the matrix behind modern software, how commercial FEM packages, like SAP 2000, implement these concepts. Interview with a software developer, matrix optimizations. Insted.pro learning objectives checklist, formulate and solve eigenvalue problems for dynamic analysis. Implement efficient linear system solvers for FEM. Apply coordinate transformations to complex structures. Chapter features, 15 worked examples with engineering significance, 8 MATLAB/Python code samples, 5 real-world case studies, 3 detailed derivations of key formulas. Assessment tools, matrix proficiency self-test, FEM problem set with solutions, coordinate transformation visualization exercise. Would you like to, 1. Add more computational examples? 2. Include specific structural engineering applications. 3. Expand the section on iterative solvers. Chapter 3, Differential equations in civil engineering. 3.1 Ordinary differential equations, odes beam deflection and vibration core theory, 2 ND/4th order odes in structural analysis, Euler-Bernoulli beam equation, EI, dW/dx, equals Q, x, free vibration equations, mx plus kx equals 0. Engineering applications, beam deflection analysis, cantilever beams under point loads, continuous beams with multiple supports, solutions using boundary conditions, fixed, pinned, free ends, structural vibration, natural frequency calculations, damped/undamped single/multi-degree systems, seismic response analysis. Computational methods, Python number Python code for solving beam ode from scipy. Integrate import solve_bvp def beam _ode, xy return np.vstack, y1, y2, y3, q, x/ei, case study, Golden Gate Bridge vibration modes analysis, solving deflection equations for stadium roof design. 3.2 Partial differential equations, PDEs heat transfer and wave propagation. Key PDE types. Parabolic, heat equation U/T equals alpha superscript 2U, hyperbolic, wave equation superscript 2U/T superscript 2 equals C superscript 2 superscript 2U, elliptic, Laplace/Poisson superscript 2U equals F, XY. Civil engineering applications, heat transfer, thermal analysis in mass concrete powers, building insulation performance modeling, underground pipeline temperature gradients. Wave propagation, seismic wave transmission through soils, blast wave impact on structures, tsunami force calculations. Visualization, COMSOL multiphysics simulation outputs. Temperature contour plots in concrete dams. 3.3 Numerical solutions, finite difference methods, numerical techniques, explicit versus implicit schemes, Crank-Nicolson method for heat equation, central difference approximations. Implementation framework, 1. Discretization of domain. 2. Formulation of difference equations. 3. Boundary condition application. 4. Matrix system solution. MATLAB example, MATLAB finite difference solution for 1D heat equation. N equals 50, dx equals L/n, dt equals 0.1, alpha equals k/rho cp, a equals gallery, tridiag n1 2,1, u equals zeros, n1, u, 1, equals t1, u, and, equals t2, For n equals 1 times steps u equals u plus alpha dt slash dx2, au, and engineering validation, comparison with analytical solutions, convergence studies, grid independence, stability criteria, CFL condition, special feature, when theory meets construction, how PDE solutions informed. The Burj Khalifa's concrete cooling system, interview, solving vibration PDE saved our bridge design, senior structural engineer chapter tools, 12 derivation exercises with solutions, 8 ready-to-run MATLAB/Python scripts, 5 real-world case study analyses, 3 interactive web-based simulators learning outcomes, formulate odes for beam and vibration problems, solve PDEs for thermal and wave phenomena, implement stable finite difference schemes, validate numerical solutions against field data assessment, design problem, develop FD scheme for soil consolidation, error analysis assignment, vibration lab with computational verification. Would you like to, 1. Add more case studies from geotechnical engineering? 2. Include parallel computing techniques for large problems? 3. Expand the section on nonlinear differential equations. Chapter 4, Probability and Statistics for Reliability Analysis. 4.1 Probability Distributions in Load and Resistance Modeling. Core probability concepts, random variables in civil engineering, load variables, live loads, wind loads, seismic forces, resistance variables, material strength, section capacity, key probability distributions, normal distribution for material properties, FC, phi, log normal distribution for load effects, extreme value distributions, Gumbel, for maximum loads. Weibull distribution for fatigue life structural reliability fundamentals, limit state functions, G, X, equals R, S, reliability index, beta, and probability of failure, PF, first order reliability method, form, applications practical implementation, Python number Python code for reliability analysis imports ip.stats as stats def reliability underscore index, mu underscore r, sigma underscore r, mu underscore s, sigma underscore s beta equals, mu underscore r, mu underscore s, slash np.sqrt, sigma underscore r2 plus sigma underscore s2, pf equals stats.norm.cdf, beta, return beta, pf case study. Calibration of LRFD factors using probability methods, comparison of safety levels in different design codes. 4.2 Statistical methods for material testing, statistical quality control, sampling plans for construction materials, control charts for concrete strength monitoring, acceptance criteria based on statistical parameters, key analysis methods, hypothesis testing for material compliance, t-tests for mean strength verification, f-tests for variance comparison, Bayesian updating for material properties, regression analysis for strength-age relationships. Concrete example, ASTM C39/C39M test result analysis, 28-day strength prediction using early age tests, operating characteristic curves for acceptance plans, visual tools, probability plots for normality assessment, confidence interval plots for mean estimates, control charts with 3 sigma limits. 4.3 Risk assessment and Monte Carlo simulations, risk analysis framework, hazard identification, probability estimation, consequence evaluation, risk mitigation strategies, Monte Carlo methods, random sampling techniques, variance reduction methods, convergence criteria, advanced applications, system reliability analysis, time-dependent reliability, spatial variability modeling, MATLAB implementation, MATLAB % Monte Carlo simulation for foundation settlement. N_sim equals 10,000, E equals lnrnd, mu underscore E, sigma underscore E, N_sim 1, Q equals normrnd, mu underscore Q, sigma underscore Q, N_sim 1, settlement equals QB, 1 nu 2, dot slash, E asterisk I, PF equals sum, settlement s_allow, slash n_sim, case studies, seismic risk assessment for building portfolios, flood risk analysis for bridge foundations, corrosion probability modeling for marine structures special feature, when statistics saved the project, interview with forensic engineer on using statistical analysis in failure investigations, case study of statistical quality control in Hoover Dam concrete placement chapter tools, 15 practical exercises with real data sets, 8 ready to use code templates, 5 industry case studies, statistical tables for civil engineering applications learning outcomes, apply probability distributions to load and resistance modeling perform statistical analysis of material test data conduct reliability assessments using Monte Carlo simulation interpret risk analysis results for decision-making assessment, reliability analysis project using field data, material testing statistical report, risk assessment presentation for a real structure optional additions, 1 machine learning applications in reliability analysis 2. Bayesian updating with field observations 3. Spatial reliability analysis for infrastructure networks 4. Non-parametric statistical methods 5. Uncertainty quantification in computational models. Would you like to expand any particular section with more examples or implementation details? Chapter 5, Numerical Methods and Computational Techniques for Civil Engineers 5.1 Route Finding and Optimization, Newton-Raphson, Gradient Descent, Core Algorithms, Newton-Raphson Method, Iterative Formula, x equals x, f, x, slash f, x, Application in Nonlinear Structural Analysis, Convergence Criteria and Pitfalls, Gradient Descent, Step Size Selection Strategies, Application in Topology Optimization, Comparison with Conjugate Gradient Method Civil Engineering Applications, Solving Nonlinear Equilibrium Equations, Calibration of Material Models, Foundation Bearing Capacity Optimization Python Implementation, Python number Newton-Raphson for Nonlinear Structural Analysis def Newton_Raphson, f, df, x0, toll equals 1e6, max_adhere equals 104 I in range, max_adhere x_new equals x0, f, x0, slash df, x0, if abs, x_new, x0, toll, return x_new x0 equals x_new return x0 case study, nonlinear analysis of a cable-stayed bridge, optimization of truss member sizes under multiple load cases 5.2 numerical integration, trapezoidal, Simpson's rule, integration techniques, Newton-Cotes formulas, trapezoidal rule, first order, Simpson's 1/3 rule, second order, Gaussian quadrature, higher precision, engineering applications, calculating section properties, A.I.S., computing work and energy quantities, evaluating probability integrals error analysis, Richardson extrapolation, adaptive integration techniques, convergence studies MATLAB example, MATLAB % Simpson's rule for moment of inertia calculation y equals 0, 1.2, 1.5, 1.3, 0.8, 0% section profile h equals 0.5%, spacing I equals h/3, y, 1, plus 4 sum, y, 2:2 and 1, plus 2 asterisk sum, y, 3:2 and 2, plus y, and, visualization, comparison of integration methods, graphical representation of numerical error 5.3 finite element method, FEM, fundamentals FEM framework, 1 discretization, mesh generation techniques, element types, 1D, 2D, 3D, convergence requirements 2. Formulation, shape functions and interpolation, stiffness matrix assembly, boundary condition application 3. Solution, linear/nonlinear solvers, post-processing and interpretation civil engineering applications, structural analysis, static and dynamic, heat transfer in mass concrete, seismic soil structure interaction practical implementation, Python number simple 1D FEM example, axial bar, import numpy as np number global stiffness matrix assembly k_global equals np.zeros, n_nodes, n_nodes, 4 element in elements, k equals, EA/L, np.array, 1, -1, -1, 1, number add to global matrix k underscore global element dot nodes. Element dot nodes plus equals k commercial software connection, comparison of ANSI, Abacus, and SAP 2000 implementations, pre-processing and post-processing workflows special feature, FEM in the real world, case study, FEM analysis of Burj Khalifa's foundation, interview, how we debugged a complex FEM model, senior analyst chapter tools, 10 hands-on coding exercises, 5 complete FEM examples with data sets, 3 commercial software tutorials, error estimation guidelines learning outcomes. Implement root-finding algorithms for engineering problems. Apply numerical integration to calculate section properties. Formulate basic finite element models. Evaluate numerical solution accuracy assessment, nonlinear analysis programming assignment, beam deflection integration project, simple truss FEM implementation. Optional expansions, 1 isogeometric analysis methods. 2 machine learning enhanced numerical methods. 3 parallel computing techniques. 4 extended FEM, XFEM, for crack propagation. 5 multi-scale modeling approaches. Would you like to focus more on any specific application area or include additional computational examples? Chapter 6, Tensor Analysis for Continuum Mechanics in Civil Engineering. 6.1 Stress and Strain Tensors. Mathematical Foundations, Tensor Notation and Index Convention, Rank 2 Tensor Representations, Cauchy Stress Tensor, Sigma, Infinitesimal Strain Tensor, Epsilon, Transformation Laws under Coordinate Rotation. Visual Representation, Sigma Tau Tau. Sigma equals Tau Sigma Tau Tau Tau. Sigma. Key Concepts, Principal Stresses / Strains, Eigenvalue Problems, Invariance, I, for failure. Criteria, Deviatoric and Hydrostatic Components. Engineering Computation, Python number. Python code for principal stress calculation. Import numpy as np stress underscore tensor equals np.array, 50, -30, 0, -30, 20, 0, 0, 0, 10, principal underscore stresses equals np.linalg.equals, stress underscore tensor. 6.2 Applications in Geotechnical and Structural Engineering. Geotechnical applications, soil stress states under foundations, Moore-Coulomb failure criterion in tensor form, anisotropic soil behavior modeling. Structural applications, stress concentration analysis, composite material behavior, shell and membrane structures. Case study, tensor analysis of a deep excavation support system, stress redistribution in tunnel linings. Field measurement connection, strain gauge rosette data interpretation, conversion of field measurements to tensor components. 6.3 Tensor calculus in nonlinear material behavior. Advanced formulations, finite strain measures, Green-Lagrange tensor, objective stress rates. Jaumann, Truesdell, plasticity flow rules in tensor form. Nonlinear material models, hyperelasticity, rubber bearings, elastoplasticity, soil constitutive models, viscoelasticity, asphalt behavior, computational implementation, MATLAB. MATLAB code for tensor operations in material model function. Stress equals nonlinear underscore material, strain, properties, fourth order stiffness. Tensor C equals get underscore stiffness underscore tensor, properties, second Biola-Kirchhoff stress. Stress equals double underscore dot underscore product, C, strain. N special feature, when tensors solve real problems. Interview, how tensor analysis improved our dam safety assessment. Case study, tensor-based analysis of the Millau Viaduct cables. Chapter tools, tensor manipulation cheat sheet, 15 progressive exercises with solutions, 3 complete geotechnical / structural examples, and CAPDL tensor operation examples. Learning outcomes, manipulate stress / strain tensor components. Solve principal value problems for engineering applications. Formulate constitutive models in tensor notation. Implement tensor operations in computational analyses. Assessment, tensor transformation problem set, constitutive model programming assignment, case study analysis report. Optional additions, 1. Computational homogenization methods. 2. Micromechanics tensor approaches. 3. Damage mechanics tensors. 4. Multiphysics coupling tensors. 5. Tensor visualization techniques. Would you like more emphasis on any particular application area or additional computational examples? Chapter 7, Fourier and Laplace transforms in civil engineering. 7.1 Dynamic systems analysis, seismic response, signal processing, core mathematical tools, Fourier transform, frequency domain decomposition, _f, omega, equals f, t, e, it, dt_, discrete Fourier transform, DFT, for digital signal processing, fast Fourier transform, FFT, algorithms, Laplace transform, _LF, t, equals f, s, equals f, t, e, st, dt_, transfer functions for system dynamics. Seismic engineering applications, earthquake ground motion analysis, response spectrum generation, structural modal analysis, signal processing in SHM, noise filtering in sensor data, damage detection through frequency shifts, operational modal analysis. MATLAB implementation, MATLAB earthquake response analysis using FFT. Excel, dt equals load_seismic_data, n equals length, Excel, frequency equals 0 and 1, slash, n asterisk dt, FFT_Excel equals ABS, FFT, Excel, dominant_frequency equals frequency, find, FFT_Excel equals max, FFT_Excel, 1 round, n/2, 7.2 Applications in vibration damping and control systems. Vibration control systems, tuned mass damper, TMD, design, base isolation systems, active vibration control transfer function analysis, SDOF system, _H, S, equals 1/, MS superscript 2 plus CS plus K, Bode plots for system response, pole zero analysis for stability. Case study, Type A 101 TMD system analysis, Fourier analysis of pedestrian bridge vibrations. Practical computation, Python number Python code for vibration analysis from scipy.fft import numpy as npdef. Analyze vibration, data, sampling rate n equals len, data, yf equals fft, data, xf equals np.linspace, 0, sampling rate /2, n/2, return xf, 2/n asterisk np.abs, yf0 n/2, advanced topics, wavelet transforms for non-stationary signals, Hilbert transform for instantaneous frequency, time frequency analysis methods. Special feature, when math meets megastructures, interview, how transform method saved our skyscraper design, case study, Millennium Bridge vibration analysis. Chapter tools, 10 ready to use. MATLAB/Python scripts, 5 real vibration datasets for practice, step-by-step FFT tutorial, transfer function derivation exercises. Learning outcomes, perform frequency domain analysis of structural responses. Design vibration control systems using transform methods. Implement digital signal processing for SHM. Interpret transfer functions for dynamic systems. Assessment, seismic record processing. Assignment, vibration control system design project, signal processing case study report. Optional additions, 1. Machine learning for automated signal interpretation. 2. Nonlinear system analysis methods. 3. Experimental modal analysis techniques. 4. Wave propagation applications. 5. Real-time processing algorithms. Would you like more emphasis on any specific application area or additional computational examples? Chapter 8, Optimization Techniques in Civil Engineering Design. 8.1 Linear/Nonlinear Programming for Resource Allocation. Mathematical Foundations, Linear Programming, LP, Standard Form, min cx subject to x less than or equal to b, x greater than or equal to 0, simplex method and interior point algorithms, duality theory and sensitivity analysis, nonlinear programming, NLP, KKT optimality conditions, sequential quadratic programming, SQP, penalty function method civil engineering applications, construction resource scheduling, transportation network optimization, water distribution system design, concrete mix proportioning Python implementation, pulp Python from pulp import * number resource allocation problem prob equals LP problem, construction _ scheduling, LP minimize, x1 equals LP variable, crew _ a, 0, none, LP integer, x2 equals LP variable, crew _ b, 0, none, LP integer, prob plus equals 500 x1 plus 750 x2 number cost function prob plus equals 8 x1 plus 12 x2 equals 100 number man hour requirement prob plus equals x1 plus x2 equals 15 number crew availability prob solve. 8.2 Topology optimization in truss and frame design computational methods, solid isotropic material with penalization, SIMP, level set methods, evolutionary structural optimization implementation framework, 1 design domain discretization 2. Finite element analysis 3. Sensitivity analysis 4. Material redistribution 5. Convergence check case studies, lightweight bridge deck optimization, earthquake resistant moment frame design, architectural facade optimization MATLAB top optcode, MATLAB %simp topology optimization while change toll FIA equals solve _ fem, mesh, x, c equals compliance, FIA, dc equals sensitivity, FIA, x equals update _ density, x, dc, change equals max, abs, x, x _ old, and 8.3 genetic algorithms and machine learning applications genetic algorithm components, chromosome representation, fitness functions, selection, crossover, and mutation operators, parallel computing implementations machine learning integration, neural networks as surrogate models, reinforcement learning for design exploration, dimensionality reduction for design space emerging applications, automated BIM model generation, construction site layout optimization, smart material design Python implementation, Python from deep import algorithms, base, creator, tools number GA for truss optimization creator.create, fitness min. Base.fitness, weights equals 1.0, creator.create, individual, list, fitness equals creator.fitnessmin, toolbox equals base.toolbox, toolbox.register, evaluate, evaluate _ truss, toolbox.register, mate, tools.cxblend, alpha equals 0.5, toolbox.register, mutate, tools.mutgaussian, mu equals 0, sigma equals 1, inp equals 0.2, population equals toolbox.population, n equals 50, algorithms.ea simple, population, toolbox, cxpb equals 0.5, mutp equals 0.2, gen equals 100, special feature, optimization in iconic structures, case study, Beijing National Stadium. Bird's nest, topology optimization, interview, how ML is changing structural design, lead engineer at Arup chapter tools, 15 practical optimization exercises, 8 ready-to-run code templates, 5 industry case studies, top opt visualization toolkit learning outcomes, formulate civil engineering problems as optimization models implement topology optimization for structural components apply evolutionary algorithms to design challenges integrate machine learning with traditional optimization assessment, construction resource allocation project, bridge topology optimization assignment, genetic algorithm parameter tuning exercise optional additions, 1 multi-objective optimization methods 2. Robust optimization under uncertainty 3. Cloud-based optimization platforms 4. BIM integrated optimization workflows 5. Quantum computing applications. Would you like more emphasis on any specific method or additional implementation examples? Chapter 9, Fractal and Chaos Theory in Civil Infrastructure Systems 9.1 Fractal Geometry in Material Microstructure Fundamental Concepts, fractal dimension calculation, box counting, Minkowski methods, self-similarity in material microstructures, power law scaling relationships, civil engineering applications, concrete technology, fractal analysis of crack propagation patterns, pore structure characterization in cement paste, D_F equals 2.3 to 2.8, aggregate gradation optimization using fractal theory, geomaterials, soil particle size distribution, D_F typically 2.4 to 2.9, rock fracture surface analysis, asphalt binder morphology computational methods, Python number Python code for box counting fractal dimension import numpy as np_def fractal_dimension, image scales equals np.log space, 0.1, 5, number equals 20, base equals 2, counts equals 4 scale in scales, boxes equals image.shape 0// scale count equals 0 for I in range, 0, image.shape 0, scale for j in range, 0, image.shape 1, scale if np.any, image. II plus scale jj plus scale count plus equals 1 counts.append, count, return np.polyfit, np.log, scales, np.log, counts, 1, 0 9.2 Chaos theory in traffic flow and hydrology. Chaos theory fundamentals, phase space reconstruction, Lyapunov exponents for stability analysis, strange attractors in dynamic systems. Traffic engineering applications, nonlinear traffic flow models, modified green shields model with chaos terms, jam formation prediction, lambda_max 0.12 bit/sec for typical freeway traffic. Intelligent transportation systems, chaos control in signal timing, anomaly detection in traffic patterns. Hydrological systems, rainfall runoff chaotic behavior, sediment transport dynamics, flood prediction using chaos indicators. Case study, Mississippi River discharge patterns, Hurst exponent H0.72, London M25 orbital traffic chaos analysis. Special feature, when chaos theory prevented collapse, forensic analysis of Tacoma Narrows Bridge oscillations, interview, predicting the unpredictable, transportation chaos theorist. Chapter tools, fractal analysis software toolkit, 10 real-world datasets for chaos analysis, step-by-step guide for phase space reconstruction, hydrological time series analysis templates. Learning outcomes, calculate fractal dimensions of material structures, analyze chaotic behavior in infrastructure systems, apply nonlinear dynamics to traffic prediction, interpret strange attractors in hydrological data assessment, concrete SEM. Image fractal analysis project, traffic flow chaos identification exercise, hydrological time series prediction challenge. Optional additions, 1 machine learning for chaos detection, 2 multifractal analysis applications, 3 quantum chaos in nanostructured materials, 4 urban growth fractal patterns, 5 chaos control in smart cities. Would you like more emphasis on specific analysis techniques or additional case studies from mega projects? Chapter 10, Mathematical Modeling of Real-World Civil Engineering Problems. 10.1 Bridge Load Distribution Models, Advanced Modeling Techniques, Grillage Analogy Methods, Orthotropic Plate Theory Adaptations, Lever Rule Applications for Multi-Girder Systems, Finite Element Idealization Parameters, OSHTO LRFD Guidelines, Influence Surface Analysis, Muller-Breslau Principle Implementations, Live Load Positioning Algorithms, Dynamic Impact Factor Modeling, I equals 1.33, 0.41 L for L less than or equal to 50 m. Case study, Golden Gate Bridge, Live Load Distribution Factors Calibration, Seismic Load Path Optimization, Temperature Gradient Modeling Effects Computational Implementation, Python import numpy as np_def grillage_analysis, n_girders, span, EI_values number stiffness matrix assembly K equals np.diagram, EI_values, number load distribution factors df equals 1/n_girders plus 0.15, np.arrange, n_girders, 0.05, np.arrange, n_girders, 2, return df/np.sum, df, number normalized distribution 10.2 soil. Consolidation and Terzaghis theory. Modern extensions to classical theory, 3D consolidation models, by its poroelasticity framework, Mondale-Cryer effect simulations, radial drainage well formulations, numerical solutions, finite difference implementation, Crank-Nicolson scheme, vertical drain modeling, Barron's theory, large strain consolidation, Gibson's equation, field validation case, Kansai International Airport settlement, vacuum preloading analysis, piezometer data. Assimilation techniques. MATLAB implementation, MATLAB %1D consolidation solver, Terzaghi, function ut equals consolidation _1D, MVCVHDTT max, dz equals h/100, z equals 0 dzh, u equals zeros, length, z, 1, u, and, equals 100, % initial/boundary for t equals 0 dtt max d2u equals div, u2, /dz2, u, 2 and 1, equals u, 2 and 1, plus cv dt d2u, and end conditions. 10.3 Computational fluid dynamics, CFD, for hydraulic systems. Civil engineering. CFD applications, bridge hydraulics, pier scour simulations, K-SST turbulence model. Deck uplift forces during flooding, debris impact modeling, urban water systems, storm sewer network optimization, combined sewer overflow analysis, water treatment plant hydraulics. Advanced modeling considerations, multi-phase flow for sediment transport, moving boundary problems, VOF method, high-performance computing implementations. Open foam case example, / pimple foam input snippet for scour transport model. Newtonian, Nu 02-1000001E06, bed type granular. Particle density 2650, packing limit 0.62, simulation special feature, when models save lives. Forensic analysis of 2018 Genoa bridge collapse, interview, how CFD prevented dam failure, hydraulic specialist. Chapter tools, 12 complete model templates, FEM/FD/CFD, 8 calibration datasets from megaprojects, multiphysics coupling guidelines, uncertainty quantification framework. Learning outcomes, develop bridge load distribution models per OSHTO standards. Implement advanced soil consolidation simulations. Configure CFD models for hydraulic problems. Validate numerical models with field data assessment, bridge grillage modeling project, settlement prediction challenge, CFD scour simulation report. Optional additions, 1 machine learning surrogate modeling, 2 digital twin integration, 3 real-time monitoring data assimilation, 4 climate change resilience modeling, 5 BIM-coupled simulation workflows. Would you like to include specific software tutorials or focus more on particular modeling approaches? Chapter 11, Advanced Computational Tools for Civil Engineering Mathematics. 11.1 MATLAB/Python for Civil Engineering Mathematics. Core Technical Computing Capabilities, MATLAB Focus, Symbolic Math Toolbox for Analytical Derivations, PDE Toolbox for Structural and Geotechnical Simulations, Parallel Computing Toolbox for Large-Scale Problems. Python Ecosystem, Scientific Stack, NumPy/SciPy for Numerical Methods, Specialized Libraries, Phoenix, FEM, OpenSeas, Structural Analysis, GDAL. Geospatial Mathematics, Implementation Examples, Python NumPy, Nonlinear Beam Deflection Solver from SciPy. Integrate import solve_BVP import NumPy as npdef beam _ode, x, y, ei, q return np.vstack, y1, y2, y3, q, x, /ei, def solve_nonlinear_beam, ei, q _func, l, bcx equals np.linspace, 0, l, 100, y_guess equals np.zeros, 4, x.size, return solve_bvp, lambda xy, beam _ode, xy eiq _func, bc, x, y_guess, MATLAB %MATLAB, seismic spectral analysis function SA equals response_spectrum, Excel. dt, periods, for I equals 1 length, periods, wn equals 2 pi/periods, I, comma u equals lsim, tf, wn2 120.05 wn2, Excel, 0 dt, length, Excel, 1, SA, I, equals max, abs, u asterisk wn2, end 11.2 ANSI and Abacus for numerical simulations, high fidelity modeling workflows, ANSI mechanical, APDL scripting for parametric studies, topology optimization, Genesis integration, coupled physics, thermal structural analysis, Abacus CAE, Python scripting interface, MDB.model, advanced material models. Concrete damaged plasticity, modified CAM clay for soils, hyperelastic rubber formulations case implementation, APDL. ANSI APDL, concrete/prep 7 ET1 solid 65 MPX 130 E3. MPA MPPRXY 1,0.2 TB Concr 1 T data 0.3, 0.5. Foot/FC ratio, solve column analysis Python number Abacus Python, automated parametric study from Abacus import asterisk from Abacus constants import asterisk mdb.model, name equals beam study, for L in 5, 10, 15, mdb.constrain sketch, name equals profile, sheet size equals 20.0, mdb.sketches profile.line, point 1 equals 0, 0, point 2 equals L0, mdb.part, name equals beam plus str, L, dimensionality equals 3_d, type equals deformable body, 11.3 BIM integration with mathematical models digital twin implementation framework, 1 IFC schema mapping. Geometry conversion, NURBS to FEM meshes, property extraction, material parameters, load case translation to live data integration, sensor data streaming, Apache Kafka pipelines, model updating via Kalman filtering, dashboard visualization, Grafana/TTK, workflow example, Python number BIM to FEM conversion pipeline import if OpenShell import numpy as npdef extract _structural_ members, ifc _file elements equals for wall in ifc _file.by type, ifc wall geometry equals wall.representations 0. items 0 mesh equals convert _to _fem, geometry, elements.append, GUID, wall.globalid, mesh, material. Wall.material properties 0. strength, return elements industry specific tools comparison, tool math strength BIM integration HPC capability Revit and Dynamo basic numerical methods native integration limited ATABS advanced matrix methods IFC import/export moderate COMSOL multiphysics PDEs CAD interoperability strong, GPU support, OpenModelica. Differential algebraic XFMI standard emerging special feature, the digital job site, case study, Crossrail BIM-FEM live updating system, interview, how math models saved $2 million on our tower project chapter resources, 15 executable workflow examples, 8 industry standard template files, performance benchmarking guide, interoperability checklist learning outcomes, develop customized numerical solutions using MATLAB/Python implement advanced material models in commercial FIA. Software automate BIM to analysis workflows validate computational models against experimental data assessment, code review of a structural optimization script, FIA model calibration exercise, BIM integrated analysis project emerging trends, 1 AI-assisted meshing algorithms 2. Quantum computing for structural optimization 3. Blockchain verified computational models 4. AR/VR interfaces for numerical results 5. Digital twin certification standards. Would you like to focus on specific integration challenges or particular software combinations? Chapter 12, Emerging Mathematical Frontiers in Civil Engineering 12.1 AI-Driven Predictive Modeling Transformative Applications, Hybrid Physics AI Models, PINs, Physics-Informed Neural Networks, for crack propagation, Fourier neural operators for flood prediction, Graph neural networks for infrastructure networks implementation framework, Python number physics-informed neural network for concrete strength prediction import TensorFlow STF from TensorFlow import Keras class pin. Keras.model def init self super init self.dense layers equals keras.layers.dense 64 activation equals 10 4 in range 8 self.physics layer equals physics constraint layer, number custom layer encoding f, x, plus lambda f, x, equals 0 def call, self, inputs x equals inputs for layer in self.dense layers, x equals layer, x, return self.physics layer, x, case study, autonomous bridge inspections, computer vision plus FEM updating, 92% defect detection accuracy, versus 68% traditional methods, real-time load. Rating adjustments 12.2 Quantum computing applications in structural analysis quantum advantage areas, material discovery, variational quantum eigensolver, VQE, for cementitious composites, 1000x faster molecular dynamics, H1-1 quantum processor benchmarks, optimization, QAOA for construction scheduling, Grover's algorithm for non-destructive testing analysis quantum classical hybrid workflow, 1 problem decomposition, QUBO formulation, 2. Quantum subproblem solving 3. Classical solution refinement implementation example, #//Q number code for truss topology optimization operation solve truss problem, W's qubits equals qubit 20, apply quantum annealing, qubits, let solution equals measure truss configuration, qubits, return classical post-processing, solution, performance benchmarks, problem scale classical time quantum time, H2, --10 member truss 2.1 SEC 0.3 SEC 100 member truss. 42 minutes 1.2 SEC 12.3 Sustainable design via mathematical optimization next-gen optimization paradigms, multi-objective Pareto frontiers, CO versus cost versus safety trade-offs, epsilon constraint method implementations, circular economy models, mixed integer programming for material reuse, stochastic optimization for recycled material variability digital twin integration, Python number lifecycle optimization framework def sustainable _design optimization, model equals create _BIM model. Add LCA constraints, model, add circularity constraints, model, result equals solve co hybrid, model, number generate ept report, result, quantum enhanced solver breakthrough case, 3D printed sustainable bridge, topology optimization reduced material by 37%, carbon-aware concrete mix design, real-time strain monitoring feedback emerging tools ecosystem, technology mathematical basis implementation level --AI. Enhanced via operator learning TRL7 quantum FEM Hamiltonian simulation TRL4 biocement op genetic algorithms TRL6 special feature, the net zero calculus, interview, how mathematical optimization achieved 53% embodied carbon reduction, case study, Singapore's digital twin for sustainable urban planning chapter resources, 10 executable Jupyter notebooks, quantum computing playground, QPanda simulator, LCA optimization template library, AI model cards for civil engineering learning outcomes, implement physics-informed machine learning models formulate quantum-ready civil engineering problems develop multi-objective sustainability optimizations evaluate emerging technology readiness assessment, carbon optimization design challenge, quantum algorithm white paper, AI model validation report Horizon Technologies, 1 neuromorphic computing for real-time simulations 2. Digital material passports with blockchain 3. Photonic computing for CFD 4. Biological algorithms for self-healing materials 5. Exascale digital twins. Would you like deeper dives into specific industry adoption roadmaps or mathematical derivations? Appendices. Appendix A, Mathematical Formulas. Quick Reference 1. Structural Analysis Essentials, Euler-Bernoulli beam equation, \, EI \frac D4W dx4 equals Q, X, \, natural frequency, \, omega underscore n equals \, SQRT \, frac Km Moore's circle, stress transformation \, sigma underscore average equals \, frac sigma underscore x plus sigma underscore y2 r equals sqrt left, frac sigma underscore x sigma underscore y2 right, 2 plus tau underscore xy2 2. Geotechnical formulas, Terzaghis bearing capacity, q underscore u equals cn underscore c plus qn underscore q plus 0.5 gamma bn underscore gamma consolidation settlement, s underscore c equals c underscore c frac h1 plus e underscore 0 log frac sigma underscore f sigma underscore 0 3. Fluid mechanics, Navier-Stokes, incompressible rho left, frac partial math v partial t plus math v dot nabla math v right equals nabla p plus mu nabla 2 math v plus math f 4. Matrix algebra for Fem, stiffness matrix assembly, math k equals sum underscore e math t underscore et math k underscore e math t underscore e dash appendix B, solved problems with step-by-step solutions. Problem 1, truss analysis given, 3-member truss with loads at joint solution steps, 1 assemble stiffness matrices for each member. 2. Apply transformation matrices. 3. Solve math q equals math f 4. Compute member forces. Problem 2, concrete mix optimization objective, minimize cost while meeting strength f underscore c g 35 text mpa solution, decision variables, w/c ratio, admixture percent, constraints, workability, durability, result, Pareto frontier plot. Problem 3, seismic response spectrum input, El Centro earthquake record steps, 1 compute FFT of acceleration. 2. Solve SDOF systems for multiple periods. 3. Plot s underscore a versus t dash appendix C, MATLAB Python code examples. 1. Finite element analysis, Python import numpy as npdef assemble underscore global underscore stiffness, elements, nodes k equals np.zeros, 2 len, nodes, 2 len, nodes, 4 l in elements, k equals local underscore stiffness, l.e, l.a, l.l, k equals add underscore to underscore global, k, l dot nodes, return k2. Consolidation analysis, MATLAB function settlement equals Terzaghi underscore consolidation, CV, H, T, TV equals CVT /H2, U equals 1, 8/pi2, sum, 1/2, 1:100, 1.2 exp, dash, 2, 1:100, 1.2 pi2 TV/4, settlement equals UH, N3. Quantum-inspired optimization, Qiskit Python from Qiskit underscore optimization import quadratic program prob equals quadratic program, prob binary underscore var, x1, prob minimize, linear equals x11, quadratic equals, x1, x12, dash bibliography and further reading foundational texts, 1 Advanced Engineering Mathematics, Krasig, Wiley, 2. Finite Element Procedures, Bathe, Prentice Hall, Specialized References, AI in Civil Engineering, John, Springer 2023, Quantum Computing for Engineers, Lapierre, Cambridge 2024, Industry Standards, Ashto LRFD Bridge Design Specifications, Eurocode 7, Geotechnical Design Online Resources, MIT OpenCourseWare, Computational Civil Engineering, NIST AI Risk Management Framework Software Documentation, ANSI Mechanical APDL Guide, Phoenix Project Tutorials Key Papers, Physics. Informed Neural Networks for Structural Health Monitoring J.Struct.ENG 2023, Quantum Algorithms for Topology Optimization Nature Comp.Sci 2024 How to use these appendices, 1 Quick Calculations, use Appendix A during design checks 2. Learning Scaffolding, study Appendix B problems before attempting exercises 3. Code Templates, adapt Appendix C snippets for your project's digital companion materials, scan QR codes 4, interactive formula calculators, downloadable code repositories, video solution walkthroughs. Would you like additional appendices on, industry-specific design charts? Unit conversion tables. Mathematical notation glossary. Software keyboard shortcuts.